can encode many useful properties from graphs, and these things can be converted in terms of some algebraic properties, and tools from algebra can also be used to get good algorithms, and it is used to get good algorithms. Okay, so just we will get into the definition of Matroids, examples of Matroids, and then go on. So first start with set system. A set system is just a collection of sets over a universe. You say example 1, 2, 3, 4, 5. So this is a set system. A can you see it? I see. Okay, next. Okay. Blue is fine, right? Okay. So I represent that as a pair. The first one is universe, and the other is a collection of sets. Okay. For any universe 2 to the u, all possible subsets of u, and this is also a set system. Okay. Example 1, 2. Okay. Now we call it hereditary set system. What is a hereditary set system? A set system with the following property: u comma f. I hope this is big, right? Okay. With if a set A belonging to f in the family and A prime subset of A, then A prime belonging to f. Okay. If the set contain at least one element, then empty set will be there, because empty set is a subset of any set. Okay. Just example 2 is also, see, example for any universe 2 to the u is a hereditary set system. But this is not, because 4, 5 is there but not 4 is there. So it's not hereditary. And the another one is like, given a graph G, the universe is the edge set of G, and the family is set of all matchings. Okay. So for example, the graph look like this, then E1, E2, E3, E4, then E1 will be there, E2 will be there, and then say E1, E4, E1, E3 will be there, like that. Look at E1, E3, it's a matching. Okay. So take any matching and take its subset, it's also a matching. So it satisfies hereditary property, right? And now comes to Matroids. Okay. Matroids is a hereditary set system with one more property. So a set system u comma f with the following property. The first one is the hereditary property, that is, if A belonging to the family F and A prime subset of A, then A prime belonging to F. Okay? The same property as the hereditary set system. And there is the other property is it is called the exchange property, which is as follows. If A comma B belonging to the set F and the cardinality of A is strictly less than B, then there exists an element in B minus A such that A union B belonging to the family. So, if I have two sets in the family, one is A and B and the other is B, and B is strictly larger size than A, then I should always be able to find an element in B that can be extended to, that can be added to A. That element B should be in B minus A, an element, a new element, and that can be added to A such that A union B is in F. Okay? So, examples. Can you pick one from this? This one? Okay. And what about this? Is it? This is not. Okay? Because this property will not be satisfied. We will see it. Let G be this graph, say E1, E2, E3. Okay? And the collection of matching I have like say A equal to E2 and B equal to E1, E3. I cannot add E1 to E2 and get a matching, or E3 to E2 and get a matching. So this is not. Okay. Now let's see another examples. A universe U, and this is also one simple example. Like, and the family is all sets of size at most say k for some positive integer k. Can you see this satisfy the third property? Will it satisfy the second property? Sorry, the first property. Clear, right? If I have, what about this property? Clearly satisfied, right? Because here I have all sets of size at most k. You take two sets A and B. If A has strictly smaller cardinality, there is one element which is in B minus A. Include it, get it. And this is called uniform Metroid. It's called uniform Metroid. And before going to other examples, another property of a Metroid is all maximum. Okay, in a Metroid, this family F is called independent sets. Okay, this is also called independent sets, and this set is called the ground set. Okay. I don't know where it comes from. Uniform. Okay. Where the word comes from?
No, I mean, I could not relate the example with the name of the.
Oh, I see. you know, why it is called the uniform Matroid? Yeah, that's the question. Why it is called a uniform Metroid? The first guy maybe called it. Yeah, maybe. Okay. Okay. Now, so just before going into another examples, we'll see one more property of, let one property of it, let u comma f be a Metroid. Okay. In a Metroid, I said u is called ground set, f is called independent set, independent sets. Each set in F is called independent set, and this is called independent sets of the Metroid. Okay. Now let F u comma F be a Metroid, then all maximal independent sets have the same cardinality. Can you see it? Because take any two, suppose not, then there exists two, then you will see A and B, and then you will contradict that A is maximal, because you will find one element from B and then add it to it and contradict A is maximal, and everything will. And that number, the cardinality of the largest independent, or the any largest independent set, is called the rank of the Metroid. Okay, rank of the Metroid. Max of A in F, cardinality of A. Right? Okay. So we saw only two symbol Metroid, right? One is all possible subsets, and the other is all possible subsets of size at most k. Now we'll see like some more examples of Metroid, and that captures many useful properties. Here for the hereditary set system, we saw like some other graph property, all matchings. Okay, but we'll see like something related to matching as a Metroid, but not exactly this one. So this is, let G be a bipartite graph. And the set system I define is over A, and the family will have like say S subset of A in the family if there exists a matching saturating S. And this is a Metroid, like we will prove it. This is a Metroid. Example 1, 2. It's a third example. Okay. So we will have A here, B here, some subset belonging to the family, which means that this subset is an independent set if there exists a matching that saturates these vertices. That means there is a matching like this. I don't care about where the other endpoints are, there exists some matching. Okay. So, can you see this property first? It's very simple, right? If there is a matching saturating this, then for any subset there is a matching saturating it. What about this one? So suppose I have S1 here and a larger set S2 here, then I should be able to find one vertex here, its union gives a set where there is a matching saturating it. Okay. Why it is true? If I pick, okay, I have a matching here. So I know that there exists one element which is distinct from this A1 to A5. So if I take that matching and I add it here, it may not be a matching because the other endpoint may hit here, right? But we can prove it using induction, it is. Let's look at the case where S1 equal to 1 and S2 equal to 2, the base case, right? So this will be look like A1 B1 and this will look like say X1 X2 Y1 Y2. Okay. One of the, okay, now if one of the edges is disjoint from this one, we are done. Okay, so I can just add it, right? Okay. So otherwise what will happen? Both of them are not, it will look like this, right? So again I will get, and I got it, right? Either one, okay, one of them is disjoint from, or like one of them will, like both of them will touch it. So one can touch here, one can touch here, which means you just take both of them, right? That's a base case, right? Yeah. So which means that A1 is there, and so what is the set here? X1, X2. It's not the matching, right? So we already saw, like if we take the ground set being the set of matchings, it's not Metroidal. Already saw, like this is hereditary but not Metroidal. Clear, right? But for the base case, it's fine, right? Now look at an induction case. Okay, so I'm just giving a proof overview. So the number of elements here are mod S, right? Mod S1. So the endpoints of the other side, the matching, the endpoints, they are also mod S1. And here it is mod S2, and here also it is mod S2, which means that there is one element here which is disjoint from here. Clear? Right? There is one element here which is disjoint from here. Okay, let this be this. Look at its other guy. If this is disjoint from this guy, I am done. Push it. If it is not disjoint, okay, which means that this is something here, which means that I delete this edge, both these vertex here as well as this guy and this one. Okay. Now I get a smaller matching where S1 reduces to S1, Y is also present here. If Y is not present, I am done. Okay. And the S2 prime will also be S2 minus Y. And I deleted both these vertices from the graph. Now by induction hypothesis, I know that I can find one element from S2 prime minus S1 prime and add to it, and in this new graph they form a matching. There is a matching saturating it. Add back this edge. Done. Right? I got a matching saturating everything. Clear? So this is the way it satisfies the. So if I take the set of edges being the ground set, it's only hereditary, not matroidal. But if I take a bipartite graph and one side being the ground set and the matching saturating the vertices in one side, this is matroidal. And this matroid is called transversal matroid. Right? Now we will see two more examples of matroid that we need to use it later in the lecture. That is called, one of them is called graphic matroid or cyclic matroid. Okay? Where let G be a graph, not necessarily bipartite, just some graph. And the ground set here is the edge set. Okay? And see, F subset of, say, I call it S. S subset of E of G is an independent set. The graph induced on S is a forest, or it is acyclic. For example, a set containing E1, E2, E1, E2, E3 is an independent set in a graphic matroid. But E2, E3, E4 is not, because the graph induced on it has a cycle. Is this property clear? Is this property clear? Is this property clear? Okay, before going to prove this property, can you tell me what is a maximal independent set in such a? It's a spanning tree if the graph is connected, right? And let's prove this property, the second one. I can rub this, right? So we have the graph G and say S1 subset of E of G such that G of S1 is a forest. 2 subset of E of G such that G of S2 is a forest. Look at graph induced on S1. When I say graph induced on S1, all the vertices and the edges S1. Okay, that is the definition of graph induced on the edge set S1. It's a graph on the entire vertex set of G and these edges. So it will look like something like this, right? This is the way S1 look like, and there will be like totally mod S1 edges. If I find an edge in S2 which is between two different connected components in this figure, then I am done, right? Just take it and add it. That's a forest. And we want to prove that there exists one such thing. Why it is true? There exists one such edge in S2 which is between two connected components. Yes.
Now for this I cannot add more than 3 or
Yes. 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 Clearly. Suppose not. Okay. Then where does, suppose all the edges in S2 are not between two connected components here. All the edges are within the connected components, right? So the edges in S2 are lying within here, and there is nothing here, and they are within here, they are within here, like that. And each connected component is a tree. The number of edges in a tree on say r vertices is r minus 1. So S1 has r minus 1 vertices edges here, S2 also has r minus 1 edges here. Similarly here, then why you are saying S2 is strictly wrong? If S2 is strictly larger than S1, at least one of the edge is between two connected. Okay? So we proved this. And this is called graphic or cyclic Metroid. Okay. Now we will see one more, which is again graph. Let G be a graph. Say for simplicity, I take it as a connected graph. Okay, and then again the ground set is the set of edges in the graph, and the family S subset of then G minus S is connected. Why this property true? If G minus S is connected, G minus S prime connected where S prime is a subset of S. Clearly, right? Because then it is a super graph. Okay? So this is true. Now the important property is this. Do you see this being true here? So what is here? G minus S1 connected, ES2 connected. So G minus S is a graph, right? It may have cycles, everything. Okay. Now, when does we say that we cannot find an edge which we will add to S1 and don't get a independent set? If which edge we cannot add to S1 and get a and being in this satisfying this property, which means that it is a cut edge, right? So the edge which when I add to S1, that means when I delete again one edge from S2 which is not in S1, it should get disconnected. Okay. So suppose G minus S2 is not connected, then what will happen? All the edges in S2 are cut edges, right? So delete the edges in S2 one by one, right? You keep deleting, and each time when you delete a cut edge, the number of connected component increases, right? And for the sake of simplicity, assume that S1 and S2 are disjoint for now, okay? Then when you delete all the edges in S2 from this graph, how many connected component you will get? Mod S2 many connected component, right? Clear? Now you just add back the edges in S1, okay? One edge can connect two connected component. Keep doing. Eventually you will not get a connected component because you add back only S1 many edges, and S1 is strictly less than S2. And what is this graph? So I started with G minus S1 and I deleted the edges in S2, okay, and I got a graph, and that graph is G minus S1 minus S2, okay, and that has at least mod S2 connected component, right? Keep adding S1. One edge can connect two components. Keep adding, and then what you get? G minus S2. It's a disconnected graph and it is G minus S2, and that contradicts this. Clear?
Why you have S2 many connected components? It is not G minus S1 is not minimally connected, right?
So, okay, I'm just assuming, okay, suppose I have an edge in S2 which is not a cut edge in G minus S1, I'm happy, right? Okay, so all the edges in S2 are cut edges in G minus S1, right? Keep deleting. All the time you delete, you increase the connected component. So how many times you delete? Mod S2, and you get mod S2 many connected components. Okay, so what is this graph? This graph is G minus S1 minus S2. Keep add back the edges in S1, right? One by one. Each time when you add, at most one, like the number of connected component decreases by one, right? And how many times you do? It is mod S1, and still, okay, so there are mod S2 connected components, and you added mod S1 many edges, and the graph will be disconnected. And what is the resulting graph you got now? S2, right? And you claimed that this is connected, and that's a contradiction, right? And this is called co-graphic Metroid. look at a maximal, okay, I just forgot to say one word, okay. A maximal independent set in a Metroid is also called a basis of a Metroid, okay. Look at a basis of this Metroid. What does it mean? A maximal set of edges, after I delete, the graph is still connected, okay. And then can there be a cycle in that graph after I delete a maximal number of edges? If I delete the maximal number of edges in the graph and it is still connected, can there be a cycle in the resulting graph? No, right? So, suppose S is a basis, right? Then E of G minus S is form a spanning tree, right? What does it mean? Here, the graphic Metroid. It is a basis of graphic Metroid. Right? Because what is a basis in a graphic Metroid where if the graph G is connected? Set of all spanning trees. Right? The set of edges which form spanning trees. And that's why the name co-graphic Metroid, right? You take a basis here and its complement is a basis in the graphic. These things can also be defined for normal graph, not just connected, but for simplicity I assume that it being connected. So, just use it for now, okay. You can think about how does it look like when it is not connected, okay. But all the things are like follow, like this is still, both of them still be Metroids. Okay. And this Metroid is called the dual of this Metroid, and this Metroid is called the dual of this Metroid. And for any Metroid we can define dual. Okay, this is one example. How to define dual of a Metroid? So it has the same ground set, and which are the bases in F star? The bases in F star are the complements of the bases in UF. So which means that any subset which is a subset of complement of some base is an independent set. and one can show that this is also a Matroid. Okay, and one of the example of this is graphic and co-graphic. Okay, you already saw it, right? Both of them are Metroids. And now the last Metroid which we want is linear Metroid. So where let M be a matrix. Then the ground set is set of columns of M, and the set of independent set is like C subset of U is independent if C is linearly independent. You know these terms, right? Okay. So can you see this property? This is very easy, right? Because if I have a linear set of linearly independent vectors, its subset is also linearly independent. What about this, right? If I have two sets where like both of them are linearly independent, then at least one of the vectors in the second set I cannot write as a linear combination using the first, right? Because it is linearly independent and has large size, and hence we cannot do it. Is it clear? Should I explain it a bit more? Is the second property clear? Yeah. Okay. So now we say that a Metroid is linear or representable if I can represent a Metroid in a matrix fashion. Okay, I will be okay. You know definition now, right? Or like a dual, I will delete. That's better. Okay. A Metroid U comma F is linear or representable if the following holds. Okay. There exists a matrix M and a bijection U2 columns of M such that S belonging to F if and only if the corresponding are linearly independent. So here we have a set, a ground set, and a family, and that we can find a matrix, or like rather than saying find, there exists a matrix and a bijection. That means like I can like map each element here to a column and vice versa, each column to an element, okay, and that is unique mapping, and that's why bijection, okay. And look at any set within the within the set of independent set, that is any independent set uh, in the Metroid, okay, and corresponding to that I have a set of columns here, okay, and that set of columns should be linearly independent. Okay, linearly okay, this matrix will be over over some field, okay, over some field, and when I say linearly independent, it's linearly independent over this field, okay, and there are like you you definitely know various field like f2 reals and fq, f2 to the p where p is a prime number, like there are finite fields, and then right, this is clear, which means that a Metroid I can represent like a matrix, and independence in Metroid translate to linearly independent. This is what I mean by we can convert some properties into algebraic properties. Like linearly independence is like an algebraic property, right? But whatever you have seen here, like there are like sets, graph, these are the things, right? And can we convert these properties, these graph set properties, to the property of being linearly independent? Okay, can you give like a representation for this? U comma 2 to the u. What is a representation for u comma 2 to the u? You know rank basis, right? Rank and basis of a Metroid. That's what u comma 2 to the u.
Number of columns to take, and one the diagonal.
So identity matrix. Okay. Good. Any set of columns are linearly independent, and all possible subsets are there, right? And what about for this? And this is bit tricky. Sets of size at most k. Okay, so I will explain. Dimension k matrix means which dimension? The number of rows or number of columns? Number of columns. But I see. I want a bijection first of all, and I want the number of columns equal to the number of elements. So I cannot restrict the number of columns to k, right? Okay. So there is a representation for it. I will explain it. Take the following matrix. Where 1 to the 0, 1 to the 1, 1 to the 2, etc. up to 1 to the k minus 1, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the k minus 1, 3 to the 0, like that. Okay? It's a k times n matrix where n equal to mod u. Okay? Now, if I have a, okay, just before going into the proof of it, if I have a k times k matrix such that its columns are linearly independent, then what all we know? is its rows are linearly independent, right? Then its rows are also linearly independent because column rank equal to row rank, okay, using that. And what you know about the determinant? If this is like full rank, so determinant of this will be non-zero then, right? To prove that this is a linear representation of this Metroid, what we need to prove, any k set of columns you just restrict, then I will get a k times k submatrix. Its determinant should be non-zero, okay? And so if I have k times k matrix, q1 to the 1 etc. to qk to the 0 etc. up to qk to the k minus 1, where each of, okay, the determinant of this will be equal to, I think it is product qi minus qj where I less than j, right? And when does this has a non-zero determinant? All the qi's are different, right? Then I will multiply with everything non-zero. So here I wrote everything is distinct, right? So you take any k submatrix, it looks like this, and its determinant is non-zero. You are done, right? You just give an arbitrary bijection from U to this, and this is over reals. You can give this representation over any field where so any fp where p greater than n. So I need n distinct entries, otherwise something will go zero here. So the field should have at least n entries. So the moment your field has at least n elements, then I have a representation for this. Clear? Okay. How will see a representation for graphic Metroid? Okay, so what we want for a representation for a graphic Metroid? We want a matrix, and the column should correspond to edges. So can you suggest some matrix, at least from that knowledge? Columns should correspond to, adjacency matrix means columns corresponds to vertices, right? Incidence matrix. Okay, so take incidence matrix, right? I have an edge E1 here, and it is between U and V. I will have one here and one here, right? Okay. Now here is an exercise. Prove that this is not a representation. Right? So this is an exercise where over reals. If this matrix is over reals, but you are, okay, we can get a representation from this itself as follows. So we have a graph G, right? Like it will be look like it is some undirected graph, okay, arbitrarily oriented. Arbitrarily orient. Now you take the incidence graph where EI, suppose EI between U to V, from U to V, from U to V, okay. Okay, we will prove that this is a representation. Is it coffee time? No? No. Okay. So to prove that, first we need to prove that when the set of edges form form a forest, like the underlying the undirected setting, then those set of edges will be linearly independent, right? Hmm? Hmm. Yeah. Yes, exactly. Okay. So at one direction he told, right? Suppose there is a cycle, okay, and assume its direction is fully like this. I oriented like this, okay. The orientation is like this. Then how does it look like? 1 minus 1, and then there is a 1 here. You take this one, and it will be 0. But I oriented in an arbitrary way. So you just need to multiply with minus 1 if the orientation is different, right? Assume that you just reorient it. What is the reorientation means? Reorientation means you are multiplying with minus 1. Okay, that is the good way of thinking, maybe.
So if there is, suppose there are two paths from vertices. One, in this cycle, take two vertices,
Okay.
and then there are two paths. This is not a cycle, but what?
No, I didn't get what you're saying. Oh, okay. That's what. Okay. Suppose it is a cycle. It's a directed cycle. Then you agree it is 0. Okay. Now, what you the problem is it's not a directed cycle, but it is an undirected cycle, which means that some edge, instead of going say from here to here, this edge is coming like this. Suppose you multiply this column with minus 1. What does it become? It actually says that I just change its direction, right? So you do, okay, I can choose the coefficients, right? For linearly independence, you just don't need to take sum, right? Sum, like it's a linear sum, right? So you can choose coefficients. So you choose that coefficient, how to change it. And so one direction he proved, right? Clear, right? Now, let's see the other direction. Okay. is only one edge. Which means that you just take this submatrix, any of these submatrix, then its determinant is non-zero, right? Okay. Now, right, this forms a forest, right, this way, right? Now, what is the determinant of? So it will have. So look at each connected component. Say, like L1 edges, L2 edges, right? And this will be like the number of vertices involved in here is, right? Now that submatrix, there I can find a submatrix whose determinant is non-zero. Look at this connected component. So there I will have how many? Sorry, L plus 1. So the idea is you just look at one of the edge which has degree 1, okay, and that will, suppose this is 1 minus 1, okay. So UV, okay, one of the column you delete, here all is 0. This graph its degree is 1, okay, and I get a submatrix whose size is, and there will have like, okay, just they will have one more row where exactly 1 is 1 or minus 1 is there, because in every tree at least determinant how it is defined, that 1 times the sum. What does it mean? That 1 times the subdeterminant of the rest. Now by you apply the induction and you get that subdeterminant to be non-zero. So 1 times a non-zero, that is the determinant. So for every connected component you get something like that, right? Clear? Now the other thing which I want to prove is the following. Given a linear representation of a Matroid M, there is an algorithm, there is an algorithm given a linear representation of a Metroid M, outputs a linear representation of its dual in time polynomial in the polynomial number of operations in F. So there is an algorithm which given a linear representation means a matrix over some field, okay, a linear representation don't call it F. Then the algorithm will output a linear representation of its dual, which means that if I gave this algorithm this output, sorry, this input, it will output a linear representation of what? Of a co-graphic Metroid, right? So the property of connectedness somehow converted into property of being linearly independent in some matrix, right? So this says like, oh, I have some set of edges, if I delete, it's connected. Now there exists some matrix, and where I look at such edges corresponding columns, they are linearly independent, and it's if and only if characterization. So one is purely graph theoretic property, and this is purely algebraic, they are equivalent. Okay, and we will also see a representation for transversal Metroid, and that will be a randomized one, and getting a deterministic one in polynomial time is notoriously open for this one. These are polynomial, right? Okay. Just one more comment here. This is a linear representation over reals. I can get a linear representation over any field where this -1 represent additive inverse of 1. So in F2, what is an additive inverse of 1? Clearly 1, right? So previously I said prove that this is not a linear representation over reals, that is important, okay? But if I delete this and I say this matrix over GF2, then it is yes a linear representation, okay? The same proof goes through. No, there are Metroids which does not have linear representation, but whatever the important ones and we use it, they all have linear representation. No, there are non-Metroids for which linear representation is not possible. That I don't know, but there are something. So Fano, what it is called, Fano plane F7 or something. There are something which cannot be represented using. I think like some Metroid over 7 elements or something. Okay. But there is one at least. Okay, we'll take after coffee. We'll see this one and then move to other topics. Okay.